Hi, this is part 5 of a playlist about the preparation of carboxylic acids. This video is about the carboxylation of alkanes and organometallics with carbon dioxide. In part 6 we'll then have a look at carbonylations with carbon monoxide. Carboxylation of polar organometallics is a common strategy for preparing carboxylic acids. The required carbon nucleophiles can be prepared in situ, either from halides or by direct deprotonation. The more acidic the starting material and easier the deprotonation, the slower the carboxylation and the less stable the final carboxylic acid will be. Neutral compounds can be carboxylated with more reactive carbon dioxide analogues. I've sketched here activated phosgene as electrophile, but carbonates, chloroformates or isocyanates can also be used. In my videos about carbon dioxide, you'll find some further examples. Let's jump right into specific examples. Here, phenylsodium was generated from chlorobenzene and then treated with solid carbon dioxide. After acidification, an excellent yield of benzoic acid resulted. If you're planning to run such a reaction on a small scale, you should be aware that dry ice stored in a Dewar container quickly gets covered with frozen water. Protonation reactions are usually around 5 orders of magnitude faster than C-C bond forming reactions, and water will just protonate your carbon nucleophile. Ideally, gaseous carbon dioxide should first be dried, for instance with a cold trap, and then led into the reaction mixture. This here is an example of diester-selective lithiation of a pyrrolidine carbamate followed by carboxylation. The expected acid was obtained in high yield. Although an enantiomerically enriched acid could be prepared with the aid of enantiomerically pure diamines, the large-scale supply of such alkaloids could not be secured in this case. Therefore, the use of a non-chiral diamine and resolution of the racemic acid by a salt formation with tetrahydronaphthylamine was chosen as final synthetic strategy. Polyhalogenated benzenes are particularly acidic and can even be metallated by alkoxides. In this example, trichlorobenzene was lithiated with lithium terz butoxide and then carboxylated in a one-pot reaction. Heating to 160 degrees Celsius was necessary, but a good yield of the benzoic acid resulted. I assume that under these conditions a complete neutralization of the lithium alkoxide by carbon dioxide occurred, but this deactivation of both the base and carbon dioxide did not seem to prevent this carboxylation. Like in the previous example, also here the starting material was just stirred with lithium terz butoxide and carbon dioxide at high temperature in a polar aprotic solvent. Twofold carboxylation occurred in high yield. It can be difficult to prepare Grignard reagents from polyfunctional organic halides and metallic magnesium. Activation with diol sometimes helps, but a robust alternative is transmetallation with isopropyl magnesium chloride. Here, this technique was used to metallate an aryl bromide selectively. Carboxylation then gave a high yield of benzoic acid, while an aryl chloride remained unchanged. Another strategy for preparing Grignard reagents is by treating ketones, esters or other organic electrophiles with a mixture of metallic magnesium and chlorotrimethylsilane in DMF. In this example, such a reaction was conducted under gaseous carbon dioxide, and the carboxylated product resulted directly and in high yield. In this example, a benzylic organozinc reagent was generated from a styrene in the presence of carbon dioxide. Nickel catalysis was required both for the formation of the organozinc intermediate and for the final carboxylation. Terminal alkynes are particularly acidic and easy to deprotonate. Still, alkali acetylides are sufficiently nucleophilic to react with carbon dioxide directly. Here, in order to enable a one-pot procedure, no stoichiometric amounts of strong base, but only a mixture of cesium carbonate and 1% of silver iodide was used to generate an intermediate silver acetylide. This intermediate required heating in DMF to react with carbon dioxide, but a high yield of carboxylic acid resulted. Aryl and vinyl halides can also be carboxylated with carbon dioxide and some palladium or nickel zero catalyst. Such reactions proceed by initial insertion of the metal into the carbon-halogen bond. Like polar organometallics, some organopalladium or nickel intermediates can react with carbon dioxide and yield carboxylates, as shown here. This mechanism implies, however, oxidation of the metal, just like in a Grignard reaction. Because these metals are way too expensive to be used stoichiometrically, catalysis requires a continuous reduction of the oxidized metal. In carbonylation reactions, which are discussed in the next video of this playlist, no such reduction is required. Here, no palladium carboxylate, but a palladium acyl complex is formed by insertion of carbon monoxide into the palladium-carbon bond. This acyl complex will react with nucleophiles present in the reaction mixture and thereby regenerate palladium-0. This here is an example of nickel-catalyzed carboxylation of an aryl chloride. As reducing agent, an excess of manganese was used. Aryl chlorides usually require bulky phosphine ligands to react with nickel or palladium-0, but here a simple triphenylphosphine complex was reactive enough. Both alkyl nickel and alkyl palladium complexes readily fragment into metal hydrides and alkenes. However, sometimes these organometallics are sufficiently long-lived for synthetic purposes. Here, an alkyl bromide was subjected to conditions similar to those of the previous example, and a fair yield of carboxylic acid resulted. In this example, a benzylic ammonium salt was metallated and carboxylated enantioselectively with the aid of an enantiomerically pure nickel bipyridine complex. No carboxylation of the aryl bromide occurred. Heating carbon tetrabromide with nickel-0 complexes can yield tribromomethyl radicals. These add to alkenes and arenes, and the resulting intermediates can be hydrolyzed to carboxylic acids. Here, for instance, heating a methanolic solution of anisole, carbon tetrabromide and 10% of a nickel catalyst to 120 degrees Celsius yielded a mixture of methyl 4-methoxybenzoate, 4-bromoanisole and only a small quantity of methyl 2-methoxybenzoate. Thus, the alkylation occurred with high regioselectivity. Yield and selectivities could be improved further by adding 30% of a substituted phenanthroline, as shown here. One rather unique reaction is the twofold carboxylation of internal alkynes. This can again be realized in a one-pot fashion with a nickel catalyst, a reducing agent and carbon dioxide. In this example, a maleic anhydride was prepared this way. Ketone enolates are less nucleophilic than simple polar organometallics and thus react more slowly with carbon dioxide. The resulting 3 keto acids are thermally unstable and readily decarboxylate upon heating. In this example, propiophenone was carboxylated by treatment with a mixture of carbon dioxide, triethylamine and the weak Lewis acid magnesium chloride. Some ketones can even be carboxylated twice. Here, cyclohexanone was first converted into magnesium dicarboxylate by strong heating with an excess of magnesium methoxide and carbon dioxide, and then esterified. One way to prepare cyanoacetic esters is by carboxylation of metallated nitriles. Instead of CO2, here diethyl carbonate was used as electrophile and sodium ethoxide as base. Again, a high temperature was required for the reaction to proceed. Unfortunately, with acetonitrile, only 10% of ethyl cyanoacetate was obtained. For other nitriles, though, this seems to be a reasonable procedure. Some alkenes and electron-rich arenes can be carboxylated with carbon dioxide under acidic conditions. Here, for instance, treatment of toluene with aluminum chloride and CO2 under pressure gave almost 40% of mostly 4-methylbenzoic acid. The yield was determined with respect to the aluminum chloride used. Also, chlorobenzene could be carboxylated this way. Instead of pure aluminum chloride, the authors used a mixture of aluminum chloride and metallic aluminum. The metal reacted with the hydrogen chloride formed during the carboxylation and was converted into fresh anhydrous aluminum chloride. This strategy lowers the overall amount of chloride waste, also in standard Friedel-Crafts acylations. Another synthetic equivalent of CO2 is oxalyl chloride. Here mesitylene was carboxylated in moderate yield by a slight excess of oxalyl chloride and aluminum chloride. In this example, treatment of a substituted styrene with pressurized CO2, ethyl aluminum dichloride and dibromopyridine as base caused clean allylic carboxylation. Without the base, the yields of carboxylic acid were much lower. So what about potential side reactions? Strong bases or acids can promote many unexpected reactions. Alkyl arenes, for instance, often isomerize in the presence of acids. In this example, ethylbenzene was even dealkylated and converted into diethylbenzene by aluminum chloride. Although haloarenes are quite acidic and easy to metallate, arenes may be formed by beta elimination. It was, for instance, possible to lithiate 1,3-bromochlorobenzene with LDA at -75°C and then prepare the benzoic acid by carboxylation at this low temperature. When a more concentrated solution of 5 grams of the lithiated arene was allowed to warm above -70°C, however, an exothermic decomposition occurred, causing the reaction mixture to reflux in less than 1 minute. A mixture of aminated benzenes and biaryls was the result. The ratio of products suggests that chloride was actually eliminated more readily than bromide. Anyway, such reactions are almost impossible to conduct safely on a larger scale. In this instance, a higher dilution was the best strategy to improve the safety of this procedure. Another potential problem is the isomerization of alkenes. In this example, an internal olefin yielded substantial amounts of a linear carboxylic acid upon nickel-catalyzed carboxylation. Here are some further references which you can also find in the description of this video. For subscribers, there is a PDF version of this presentation under the Community tab. The next video of this playlist is about the carbonylation of alcohols and various halides with carbon monoxide. So long.